Hi there. Whether it's a knock at the door, a phone call, or something else, interrupts are part of everyday life. This is also true in computers. Interrupts are an important capability that help with the smooth running of your computer system, and this includes smaller systems like Arduino. So hi, my name's Glenn, and welcome to All About Arduino. Judging by the number of posts I've seen lately on social media, there seems to be quite a bit of interest, but also a bit of mystery around interrupts. So this video is about interrupts. We'll look at how they're used in Arduino, how we can use them for our own stuff, including looking at a couple of projects that I've done myself, and some thoughts that maybe people sort of think are a good idea, but perhaps not the best use case. And this video is intended to be follow along, so I've got a couple of little projects that I sort of put together to try and illustrate the concepts. And because it's Arduino, we can get down into the nuts and the bolts and really look at how they work and how we can use them. Now this is a bit of an advanced topic, but I've tried to keep it at a sort of intermediate level with some relatively simple projects that we can follow along, and I've published all of the projects on my website. If you find this video of interest, consider liking it and subscribing and turning on notifications so when I post new content you'll find out about it. And also, if you could, to sponsor me on Patreon or buy me a coffee. So with that, let's get started and have a look at interrupts on All About Arduino. So what I'll do is I'll start with a little bit of theory about what interrupts are and how they are implemented on Arduino. So an interrupt is a signal that, well, as its name implies, it interrupts the normal flow of your program. So in real life, examples of an interrupt might be a fire alarm, a telephone, or a door knock, or whatever. When those things happen, you stop what you're doing, you deal with them, and then you come back to what you're doing. So it's the same in computers, not just Arduino, but all computers. And the interrupt is dealt with a piece of code that's known as an ISR, which stands for Interrupt Service Routine. And when the ISR is completed, so it's done what it needs to do, the program resumes the normal operation. So just like what would happen if you had a phone call, you stop what you're doing. When you finish with the phone call, you disconnect and just go back to what you were doing. Okay, so let's look at a very simple example. So we have our normal program. So this is the loop. It's got some code. It's just doing its thing. Whatever it does, it just keeps going around in circles. It just does what its thing is. And then over here we have an ISR, which looks just like a regular C function. And it does what its thing and it returns. So what happens is the code is executing and it's just sort of chugging along, and then something will happen that causes the interrupt. We'll look at what those somethings are a bit later on. And so whatever happens, let's say it just happens about here somewhere, it will interrupt this code. So it's doing what it's doing and suddenly get interrupted, and it'll just suddenly start doing this. You have no visibility of that over here. This just happens. This does its thing, and then it returns, and then stuff just continues from where it left off. Now it's important to note, and I'm implying here that when this statement is finished, that the interrupt occurs and then it returns here. The interrupt can occur at random at any point in the program, including in the middle of the operation. So for example, these are unsigned longs. They'll require multiple machine instructions, and an interrupt can occur after the completion of any machine instruction. And because this subtraction here might involve multiple machine instructions, an interrupt can occur in the middle of the subtraction, which is important to remember or think of, because if the ISR, for example, modifies the previous milli's heartbeat or the current milli's, which this one doesn't, but if it did, it could randomly change some values unexpectedly. So there's an illustration there. We have the interrupt happening here. Once again, it's in the middle of the subtraction. It calls this, and then it returns back to here. Okay, so that's interrupts. So here's some characteristics of them. As I said, it can interrupt the normal flow of the program at random. The best use case is you use them for urgent matters, and we'll sort of look at what some of those examples are. It's something that needs to be done now. An ISR should be short and sweet. You don't want to be doing a whole bunch of other things. You want to make it finish, do what it needs to do and finish as quickly as possible. And to that extent, there's a few things that it should not do normally. So operations that rely on interrupts to work, and we'll look at an example of that and why that's important. And so there's some examples, serial.print and things that perhaps rely on millis to tick over, because millis relies on interrupts to count time, or potentially locking or lengthy operations. So serial.print is a little bit complicated, but that could block if you send too much. And what do I mean by block? It means when you want to print something, it doesn't have enough space to remember what you want to print, which it would normally do, and then return. But if it doesn't have enough memory to remember what you want to print, it will actually wait until space is cleared, and it kind of relies on interrupts to be working for that space to clear by itself. And similarly, you don't want to do complex calculations for the slightly different reasons, but the same sort of idea. So different events have their own interrupt vectors, so have a look what that means in a minute. And some CPUs have interrupt priorities. Most of the 8-bit ones that we work with in Arduino don't, but some of the more advanced ones like the Uno R4 MCU, it does have some levels if memory serves, which means that some interrupts can interrupt other ISRs. So what are interrupt vectors? Well, it's a little bit of a technical subject dealing with interrupts, and you have to understand a little bit about how the CPU works and the capabilities of the MCU. And this is a page from the data sheet which lists the vectors available for interrupts on an ATmega 328P, which is the MCU on an Arduino Uno. And we'll look at these ones that I've marked. So external interrupt, a timer interrupt, and I'll try and sort of go through the USART, which relates to the serial.print line. But this is what the vectors are, and it tells you what things can trigger interrupts if you choose to hook into them. Okay, and so implied in the previous point, interrupts are generally disabled while the ISR is active. So what that means is that if your ISR is active, then other interrupts won't fire. They will be remembered and they'll be stored or deferred, and so when your ISR is finished, it will then activate it. But if you're relying on something to happen that depends on interrupts to occur, such as time ticking over, which is the millis thing, then that could create a bit of a problem, or what's called a deadlock. Okay, so let's get started and we'll have a look at the first project. Okay, so this is the project that we'll be using. As you can see, it's there's a couple of LEDs and a button on it. I'll just quickly bring up the circuit diagram. So there's our circuit. As I said, you can see there's a couple of LEDs, a green one and a red one with a couple of current limiting resistors, and there's also a standard push button. And so what I'm going to do is I'm going to use the green LED as a heartbeat, and so what we'll do is just sort of set that up so it just continually blinks at a regular interval. And so the idea for that is to sort of see when the interrupts are working, or when things sort of go a little bit haywire and maybe we do need to have the interrupts enabled. And then the red LED is just going to be responsive to button pushes, which sort of reflect the interrupt being received. Now, I'm going to use the button to trigger some interrupts in here. That's not normally a good use case. There's no real reason why you'd need to do that with an Arduino. The Arduino is just sufficiently fast that, and compared to human response times, that you don't really need to worry about triggering interrupts. But I will look at another project involving communications between two Arduinos where it is actually useful and, depending upon the use case, important to intercept signals coming in through that, in this case, yellow wire or the button pin in this connection here. So that's the hardware. We'll look at getting some code up and running and get some of these LEDs doing their thing. Okay, so we'll start by getting the heartbeat LED blinking, and I just use the standard program here, blink no delay. Where's it gone? There it is. I'll just save that first. So I'll put it in all about Arduino, perhaps create a new folder, button, no ISR, just to start off with. And so just get rid of a lot of this extra stuff here. So we don't want any of that. That's going to be on pin number 7. I'll rename this. We don't want an LED state. We'll just do that a bit simpler. Heartbeat, previous millis, place all, and what else? This one, heartbeat interval, replace all, and we'll make it blink a little bit faster. I'll also initialize the serial monitor. Alright, and then so we still want to save the current time. Don't need to do any of this stuff because we'll do it all in one operation here. Okay, so we check COM12, that looks good. Arduino Uno, that looks good. So upload, and with a bit of luck, we should have a green LED blinking. Don't need that anymore. Have an error. Don't have enough closing brackets. Make this taller. That looks better. And there we have our heartbeat LED blinking. At the moment nothing's going to happen with the button because I haven't put any code in for that, obviously. That's what we'll do now. So what I'm going to do is make it so that when I push the button, I'm going to have a counter, and I'll count the number of times I've pushed the button, and that I'm going to measure that by when the button transitions to low, and then each time I push the button I'll toggle the status of this red LED here, and the LED is connected to pin 2, so I call that the system state LED. Okay, so we just add some stuff to define the LED. Oh, sorry, that's 4. So we're going to start out with the system state, which is basically the LED state, and that will be low. And then we'll have a counter, which will initialize to 0. And I've set these up as global variables because later I'm probably going to use an ISR or maybe a function to display them. Otherwise it would be better to probably put them as static variables here. But for now, for simplicity, I'll just put them there like that. So I also need to set the pin modes. Now, because I don't have a current limiting resistor for the button, it's just directly connected to pin 2. But you still have to have a resistor, otherwise that would be a floating input. So all I'll do is use the pull-up inside the MCU, is defined by input pull-up. I'll just put that print message in there so later on we don't get a bit confused as to what version of the program we're working on. Okay, so this is the logic that blinks the heartbeat. So that's fine as it is. What we'll also need to do is just check the button. Now, if we've changed state, so that could be a press or a release, then we'll remember that fact has occurred, but then further we'll check to see if it's gone low. But for this to work, we also need to remember what its previous state is. So we'll set this to high, because that's what the input pull-up will initially give us. We also need to save that so we can check next time around if the button has changed. And then what we'll do is we'll check to see if it's low, meaning the button has been pushed. Now, if it is low and the button has been pushed, then all I want to do is invert the, what did I call it? System state. All I want to do is invert it for now. And then a little bit further down, what I'll do is I'll check to see if it's changed. Now, I could do this stuff in here because that's the only place it will change. But later when we move to the interrupt version, it will need to have this logic here. So it's just a little bit easier and convenient to do it like this and just sort of break it out. So I do the same thing as the button. If the current state is not equal to the previous state, so I need to, in this case it will be low because that's what we started out here. The system state will be low, the LED is off. Then what I want to do is, well, first of all we need to remember that. So once we've processed the fact that it's changed, we don't want to do it again, so we need to remember that it has changed. And what I'll do is increment this counter, and then I'll simply print out, first of all I'll digital write, what did we call that? System status LED pin. So we'll set the LED to the current status, and also have some print routines here as well, which I'll just copy and paste. So I'll output the fact that this is the no ISR program and the system state has changed, and the counter is currently whatever the counter happens to be now after we've just incremented it. Okay, so I think that's all we need. I'll just upload that. Probably want to open the serial monitor. There it is. So there's our startup message, button no ISR, and if I push the button, then you should see that the counter increments. Now sometimes if I don't push it very well, we might see, yeah, there we go, a couple appeared just then. This is a pretty good quality button, so it doesn't happen very often. But you can see here there was two that happened in quick succession, 0.03 of a second apart. I think there was another one up here somewhere. Yeah, this one was 0.707 of a second. Yeah, so it's possible to get a few happening at once. That's called debounce, or bounce of the button, and it's an electrical artifact. And I'll look at how we can sort of maybe address that in a sort of cheating way, not the proper way, shortly, because that will then lead me into a potential problem that we have with the interrupt version. Okay, so that seems to be working. Looks like we're doing what we need to do to see it happening. So let's switch this over so it uses interrupts. So I'll just save a copy of it, and since we're going to use interrupts, I think I'll call it button ISR. I'll just open up the old one so it's handy in case we want to refer to it and compare it side by side. So I'll just put him. Okay, now we don't need to change very much. One thing that we won't need to do is any of the logic to do with the button. So you can basically get rid of all of this. And what our function will do is this. So I'll copy this. So I think what I'll do is call my function this, and there's the code. That's all we need to put in there. The other thing that we need to do is we need to link that function to the interrupt. And there's an API called AttachInterrupt. You can look at this online and have a bit of a read about it. I won't go through it here. I'll just explain how we're going to use it. But you can see here, this is the syntax, this is the recommended syntax here. We basically do attach interrupt, then we call this other function, digital pin to interrupt, and give it the pin number, and then we give it the name of the function, and then we give it the mode, which is what activity do we want to have an interrupt trigger. And since our button is on the pull-up resistor, and previously I was wondering when we press the button, which will make it convert to low, that was called a button, that was what we defined as a button press. I would want falling in this case. So digital pin to interrupt, and it's the button pin. It should also be borne in mind that not all pins support interrupts. and the characteristics on some of them are slightly different, so you definitely need to refer to the documentation. And this gets back to what I said earlier about it's a little bit technical, and you do need to understand what's going on when you're setting these things up. Now the ISR that we're going to use is this one. As you can see, there's no parameters, it doesn't return anything. It's just something's happened, deal with that something. And so there's no ability to pass parameters or return anything because there's nowhere for the return value to go, and similarly there's no ability to sort of obtain some information around it. It's up to the ISR to do what it needs to do to collect any information that needs to collect and manage it. And then finally falling. And I think that's all we need to do. So the pin modes are the same. I would probably want to change that because the whole point of putting that in was so we didn't get confused. If we don't change that, then we will get confused. Otherwise it should be the same. So let's upload it and see what happens. Okay, so now when I push the button, it seems like we have a little bit of a problem because it seems to be registering a lot of presses, or not registering them. And if my button isn't so good at quality after all, it has started to fail. But anyway, you can see that it's still happening. And you can see that the counter is incrementing, even though there's nothing in here that's, oh, I forgot to get rid of that. That's the bit that we don't want. So we get rid of that. I did actually remove it, but then reinstated it, which was silly because then I forgot to do it. And that was only so I could just copy and paste that. So that logic was probably interfering with it a little bit. Okay, so it should work better this time. So I push the button. And you can see there's already a few times when it was double registering. In fact, it seems to be happening quite a lot. But you can see there that even though there's no logic in here to do with checking the status of the button, it's still changing the system state, which is then causing this to trigger because the system state just mysteriously and randomly changes as far as the loop is concerned, which is just continually doing this. And it changes, so it increments the counter, updates the LED and prints out the message. Okay, so just upload this one again. This is our no ISR version. And we'll see if we can get that bouncing problem to occur again. It's probably a little bit less. Oh, there's a couple there that happen. It's a little bit less likely to happen here because of the print statements. But let's see, there was one, I think I saw a couple come up very quickly. Here's one, maybe 0.3 of a second. Anyway, there's a few that happen fairly quickly. So the typical way of resolving that is to basically let it settle. So when we detect that the button has gone low, just sort of let it settle for a little bit, because what happens when it's bouncing is you push the button down, but the electrical contacts sort of jump up and down due to I guess the shock of the contact, and then eventually they'll stay settled. But if you check too quickly, then you can actually detect that going up and down and then register multiple occurrences, which is what's happening when we get that repeated problem. Now, a simple cheating way of doing it is just to put in a little bit of a delay here. So I'll just delay for 50 milliseconds and upload that. And it should be almost impossible to cause that to occur. Okay, so if I do it now, you see that's pretty reliable. It doesn't seem to jump very much at all. It's just one per press. So that sort of seems to fix it. Now what I'll do though is, rather than using the delay function, I'm going to expand that out a little bit and create my own version of delay. And I'll just copy and paste that. I think I put it here just before setup. And what this is doing is it's getting the start time when we call it. Oh, sorry, you pass in the period that you want to delay, so that's 50, in this case it'll be milliseconds. So then it gets the starting time. Probably don't want to do that. Oh, no, I don't want to do that. And then all it does is, while the current time minus the start time is less than the duration, just do nothing. So it's just throwing away time, which is basically how the standard delay function works. It's not quite exactly how the standard delay function works, but it's just to sort of illustrate the purpose, and more importantly, when we look at the interrupts, why this is actually a bad idea to do this. Alright, so I'll upload it. So it should still see it's one press, one message, and that does seem to be the case. Okay, so now what I'll do is I'll copy this and put it over here. Now, what we can argue is that we've got that bouncing problem here, and if anything it's more susceptible because the button is going to be interrupted. It's not going to be delayed by any of this print rubbish down here, which is what's going to happen here, which is partially why this one behaves better in terms of the bouncing of the button. So what we can do is we can argue, well, while we're in this ISR, interrupts are disabled, so if I delay in here, then it won't be able to generate another interrupt because of the bounce. Okay, so hopefully that makes sense. We'll be wrong, of course, arguing that, but let's argue that anyway. So it's the exact same function, because I've just copied it from this version, wherever it is, up here, and put it there. And I've just copied that, and I call that in the ISR. So I'll upload that. This is where the heartbeat LED is going to come into play, because what we should see is when I push the button, the system will hang. Okay, so our heartbeat is blinking, and I push the button, and boom, it's stuck, and that's never going to recover. Now the CPU is still running, and what it's doing is it's done this. It's got the time, and then it's comparing the time with the start time, and it's going to keep doing that until we've passed the 50 milliseconds. Now that's never going to happen, and the reason that's never going to happen is because millis requires interrupts to count time, so it's sort of interrupted once every 1,000th of a second. It's actually faster than that, but it counts every 1,000th of a second. But because interrupts are disabled because we're in this ISR when we called it, the millis isn't going to get that like clock tick, and so it can't count. It never increases, so it's stuck. It's stuck at the same time as the start time. So this expression here is always going to evaluate to 0 because the millis can't move on, and that's less than the duration, so it's going to be stuck in here forever. Now if I reset, the LED started blinking again, and we're stuck. Now I did have a print line in here, so what I can do is I can say something like serial.println. I deleted it, I should have just commented it out anyway, in my delay, and we'll upload that and see what happens. So while that's uploading, just have a bit of a think about what you think will happen when we see this, bearing in mind that println also relies on interrupts. And I know we haven't looked at that yet, but it does rely on interrupts. So we'll push the button, and sure enough the green LED has stopped. But what's happened over here? So we've got in. In fact, what I might do is I'll put an underscore just to make it extra clear what's happening, because it could be that we've got in and a space. Okay. So I've pushed the button, and as before, the heartbeat has stopped, and we've still only got in. And that's to do with the way that the serial object works and how it uses interrupts. But essentially what's happening is this message is here is being stored in a little buffer, and what happens is if the communications is not doing anything, or it's ready to receive the next character, it'll put the first character in, which is the I. The instant that that happens, it's empty. The hardware takes that character and starts sending it off to wherever it sends it, and so it's empty. So there's an opportunity then to put the second character into the hardware, or the UART, or is it a USART? Whatever, a USART or a UART. And so two characters are sent to the hardware ready for sending. And when it's finished sending, or basically when the data register is empty, because it started sending the character that's stored up in it, it'll generate an interrupt that says, hey, give me the next character. But because interrupts are disabled, we never get that next character, and that's why we just get two. Okay, so we'll move on now to a little bit more theory, and then we'll move on to some use cases that sort of make sense for using interrupts. As I said, using interrupts for buttons in this way, I mean, obviously you can do it, but there's really not much point, because the no ISR version was definitely fast enough to catch all of the button presses that we were going to make. Indeed, it was too fast, because we would get that bouncing problem, which we then had to try and eliminate by introducing a delay. And again, I'd suggest using a delay is not the right way of doing it. What you need to do is actually have another if statement down here, which detects if the button state hasn't changed after a period of time has elapsed. And so there's a few examples in the Arduino IDE where you can look at that. I don't think they all do it that way. But like things like Debounce, you could look at some of those and sort of see how that actually works and do it properly. So before we move on, I just want to touch on the volatile keyword, which is a keyword that tells the compiler that a variable's contents can sort of change randomly and unpredictably, and that affects certain optimizations, or the way the compiler interprets the code and then outputs it. So now this variable here, system state, that's one that is effectively dynamically changeable. It'll change randomly. When we happen to press the button in this button ISR code, then it'll read the current value and negate it. Now for this simple program, it doesn't really matter probably, but it can have an impact, and it's a good habit to use the volatile keyword. So it's just simply a modifier to the declaration of the variable, and all we do is, well, first of all we have to find it, there it is, and type in the word volatile. And so that just simply tells the compiler, and it's lowercase, not uppercase, volatile. And that simply tells the compiler that this variable can change randomly, and usually it's due to this ISR. It can also be because of a threaded or multi-threaded application, which we don't have in Arduino IDE, or maybe the operating system, which also we don't have in the Arduino IDE. Arduino environment could change something, but it can change due to interrupts, and so it's useful to have that there. So I just comment this line of code out, which is causing our application to hang, and try uploading him. Just double check everything. Yep, that's still okay. So basically what the volatile keyword does is tells the compiler that whenever you reference this, you should always get it out of memory and not optimize any code out or anything like that. So it makes it a little bit slower, but what we're talking about is, you know, fractions of a microsecond slower than if it was the compiler was allowed to optimize it. Okay, so it's uploaded it, and as we can see, it's the serial monitor. There he is. So as you can see, it's still working, but we do have the debounce problem back. Yeah, so let's move on and have a look at some real-world examples. So the Arduino environment and a project that I've previously set up and why I've used interrupts in that. And then after that, I'll move on to a couple of other simple programs that show some good use cases for how interrupts can help the operation of the program, and in one case is actually almost essential for the smooth operation of the program. So we've sort of looked at millis, although I haven't looked at the code. We'll actually build a timer interrupt one, so not really necessary to look at that at the moment, but just take it on good faith that it uses interrupts because you don't have to do anything to make the millis update. But we'll look at some other examples, real world examples. So I'll start with the hardware serial, although it is a bit complicated, so hopefully it's not too over the top. Okay. So this is the hardware serial source code. You can actually see these for yourself, that they're available on GitHub. It's not that hard to find. I'll put a link for where this code is in GitHub so you can see it, but it's also on your PC as well because the Arduino IDE actually compiles this when you compile your program. That's what's happening in the output messages that you would have seen at the bottom section of the IDE. But this is how we define an interrupt service routine. Now I know in the previous code we used AttachInterrupt and just gave it a regular function, but behind the scenes AttachInterrupt has code like this where it says ISR and then there'll be a name, and so that name is based upon what we saw in this interrupt table of vectors. So I think it was the USART UDRE, or it might be USART TX. So USART UDRE vector, that's the one there that's being used on this particular CPU. And then the body of the function is just this. So effectively what's happening there is the code will look like this. If I take all that conditional compilation out, obviously you don't want to do that in real life, but that's what the function declaration is like. And all it's going to do is call this TXUDR empty IRQ. Now I'm definitely going to revert so I don't inadvertently save that. Yes, I want to discard the changes. And so yes, it's going to call this TXUDR empty IRQ. And that's defined over here in hardware serial.cpp. There it is, TXUDR empty IRQ. And it's the same sort of function declaration as before. It returns nothing, it takes nothing. And then what I said before was when you do a serial.print, it stores the characters into a buffer, and that's this transmit buffer. So what you send gets stored in here, and then this thing will pick off the next character when it can. So this line of code here is getting the next character that's sent, and then what it's doing is working out where the next character is going to be. So it basically is incrementing the pointer by 1 and then wrapping around back to 0 if it gets to the end of the list. And then this thing here, this is the important bit, *_UDR equals C. So what this is doing is sending or putting the character that needs to be sent into the hardware called the UDR, which I think is the USART data register. That's what that stands for. And then the hardware will just automatically take over the process of sending it. Then it does a few other things, but one of the things that's probably important is that when it's emptied the buffer, so it's sent the last character, it's executing this, which will disable the interrupts, because once it's finished sending it, there's no reason to keep saying, you know, give me more, because there's no more until you do another serial.print line. But otherwise, once the character has been sent, it then interrupts this. And so if I sort of get time or feel it's sort of appropriate, I might show a routine that has a large print. And it is a bit difficult to see, but you can actually see the LED start blinking again after a pause when you send a huge amount of output. And the reason that's happening is when you send a huge amount of output, you fill up this buffer very quickly. And as I said, the serial.print blocks, meaning it has to wait until, well, effectively this has peeled off some characters from the buffer and allows it to return. And so what you see is when it's sent enough data and the remaining print messages can fit into the buffer, then the print line will return and then the LED will start blinking again. As I said, it's a little bit hard to see because it happens very quickly, so I might not include that, but that is something you can do. And when I put this code on the website, I'll put both examples so you can try both at home if you want to. Now, how does this UDR get set? It's probably not terribly important, but it's set in here. This is the constructor, and one of the parameters is the register that you want to send, and this is just storing it in the underscore UDR. And then the constructor is called here, hardware serial, here it is, and it's given the pointer of an address of the UDR0 or UDR. And if we go back to our data sheet, so there's our data sheet, and we go to USART0, and then somewhat weirdly in equation 1 we can see the register descriptions, and then there's our UDR-N, so ours was UDR0, and so this is the transmit data buffer register. And then this somewhat confusing sentence, or at least confusing to me, the transmit data buffer register, which is the TXB mode of this UDR0, will be the destination for data written to the UDR register location. So what that means is if you put something into here, then the system will just start sending it for you. If you read from it, then that's actually the receive buffer, so the hardware sort of makes a distinction between reading and writing. And what that means is, unlike normal registers where if you write something in there and read back you should get the same value, if you write something in here then it sort of disappears, and if you read it back then you've got just whatever happens to have come in from the outside world. Looping back around to the interrupt, we can see from this section here, when the transmit buffer is written to, basically the UART will take that data and start sending it if it's not already sending something. But when it takes the data out of this UDR register, that will trigger the UDR-E or UDR empty interrupt. And looping back to the code, yes, we can see it there. Let's make that a bit bigger, we can see it there. So this is where we enter into the code. So when the UART or USART takes the data that we've sent to this register, which is the data to be sent to the outside world, it sets the flag, this UDR-E flag, but it also triggers this interrupt if it's configured. And then what happens is it calls this TX UDR empty IRQ function, which we already quickly had a look at, and what that does is takes the next character and puts it into the UDR register ready for sending, and then this simply returns. And so then the cycle just repeats itself. When the previous character is finished sending, the USART will take the next data, which this code has just written into the register, and put it into the internal workings of the serial transmission, and then it'll raise the interrupt saying that the register is empty, which basically means to the code you can put the next byte of data in and send it. And that process repeats until this buffer, this TX buffer here, is empty. So that's the very, very brief overview of the hardware serial. But what's another practical real-world example that you might want to use it for? So one example where I've used interrupts, and I've used a timer interrupt, is in this clock. Now what this is doing is sort of a countdown clock. It's showing you the time, and this is the number of days to an event. So it's an event countdown clock. I built this when we were under quarantine for coronavirus. Now when I was building this, I only had individual 7-segment LEDs. It wasn't a smart display that you communicate with and just sort of send it your data and it manages it by yourself. I just had these individual LEDs which I had to manage myself, and that's why there's so many wires connected to it. So I scroll down a little bit to the circuit diagram. This is the version I started from. This is the version of the circuit in the above clock, because it's well, it's version 2, so obviously it's got more stuff in it, but the part of the display is the same. And what's happening here is that, just click on that, I don't know if it's easier to see, but you can see there's these letters here. These are current limiting resistors for each of the segments in the LEDs. That's how LEDs, 7-segment LEDs work. This one is typically segment A, this is segment B, I think that's C, D, E, F and G, and then you have a decimal point. And this one in fact has an extra one, which is the colon, which is this L1, L2 thing here. And so the way you make it work is you, just like any other LED, you turn on different segments, and depending on which segments you turn on, you can make digits. Now, these are what's called a common cathode, and so what happens is these 4 wires coming out here with the, what do you call it, the dotted or white alternating white and colour, select the individual segment. So the way this works is you output a digit, so it might be a 1, which would be, so A and B, so that would be A and B high and the rest low, and then you select which one where you want that to display. So it's only displaying one at a time. And then what you do is you keep outputting digits very quickly in succession, so this one, then this one, then this one, and then this one, and then you update the selector to make sure that it's just displaying that one. So if you want to display 1, 2, 3, 4, then you could output 1, which would be A and B high, and then probably pull this one low with the rest being high. So technically only a 1 is displayed here and the rest will be blank. Then if you want to display a 2, which would be, I don't know what segments that would be, but whatever the segments are, you would output a 2, make this one high, so this digit goes blank, and then pull this next one low, so now technically only this one is active. And so if you do that quickly enough, it looks like the display is steady. Now, why do you want to use interrupts? Well, the reason is because other stuff is happening, and that could interfere with it, and we'll see this happening in the next section, the next example. And if you don't use interrupts, then what can happen is this can start to flicker if it's printing as messages, or it's communicating with the clock module, or sending data to a Wi-Fi server or something like that. Because this isn't getting serviced, it'll start to flicker. And so through the use of interrupts, what can happen is I can just very regularly, very frequently, very reliably just simply keep looping through here and displaying the digits. Now if you're interested in seeing how that works, let's go back to 100%, then you scroll down here to step 3, and bear in mind that the code is designed to work with this more advanced version, which has has a dimmable, an automatic dimming capability, which the first version didn't have. So in step 3, the code, there's a module here called clockdisplay.h and clockdisplay.c. So this is where the clock stuff is happening. I won't go through this, you can read this by yourself if you're interested, but this is where it's being set up. And so this is the ISR, strobe clock LED. Actually that's not the ISR, this is the interrupt service routine, which simply calls strobe clock LED, and then what that's doing is it's just essentially setting up the next digit depending upon what's in the clock display. So other parts of the program set up the clock display. Okay, let's see if we can't have some insight into how these interrupts work. And so what I'll do is set up a little test program and see if we can visualize what's going on with the hardware serial, at least the serial I/O in relation to that. So I'll start with a new program. I might just save that. Let's call it serial monitor. What we'll do is make it so that when I push a button, we'll send a bunch of messages to the serial monitor, as in this window here. We'll time how long it takes to do that job, and we'll also light up one of these LEDs while that whole print process is in motion. And before we run it, I'll try and remember to explain what's going on. So we'll declare some variables first. LED pin equals, let's use 7. So what's that? That'll be the green one, I guess. Const int button pin. That's a 2. Now, normally I like to use 115,200, but this time I'll use a slightly slower speed, 9600, and so what that means is I'll need to change this as well. So 9600. So we'll comment that one out for now. And a welcome message. Set up our pins. Don't have a resistor, so we use the input pull-up. Okay, and then all I'll do in the loop is I'll just simply say if digital read button pin equals low, then we'll run our test. Okay, so the effect of this will be that if I push the button, it'll execute this run test function. And if I hold the button down, then it'll just keep running it. So it'll be kind of like an auto repeat. Now, I have prepared this run test a little bit earlier, so I just copy and paste that in. As I said, if it's only 1 or 2 lines, I might type it, but for ones that are a bit longer, probably do it like that. Okay, so what it does is it sets the LED pin, so I think we said that was the green one, to high, so it'll turn it on. It'll register the start time of printing this message, and then it'll capture the end time. It'll work out the elapsed time by subtracting the end minus the start in this prev time. So basically it'll tell us how long in milliseconds it's taken to, in air quotes, print this message. Now, then what I'll do is for repeat in this loop for 10 times, that's probably a little bit too many, but it is good enough. I'll repeat the same process, and what I'll do is I'll get the start time, then I'll print out this, which should print the loop iteration number. So this is message 0. And then it'll, in this case, I will be 0, so it'll print 1, and it'll say previous message, and then what the previous time was. So we haven't recalculated previous time yet, so the first time around, it'll be the time that it's taken to output this message number 0. It'll print that time, and then milliseconds elapsed. And it's a little bit verbose because remember I mentioned that the print line puts its data into a buffer, and so I want to illustrate the buffer filling up. If memory serves, and you can look it up in the hardware serial files, and if memory serves, the buffer of messages on an Uno is 64 bytes, which means we can store 64 characters, not forgetting that this would count as a character as well, because the new line is a new line character. Anyway, so it prints that message out, calculates the end time or extracts the end time, and then it calculates the previous time for this message that it just printed when I was, in this case, 0. So now we're replacing that value with the first message. So now we've got the elapsed time for message 0, which will display as 1. And then I will become 1, so it'll print 2, previous message, and now it'll print the previous time that it took for the first of these messages to print. So it'll do that 10 times, and then it'll turn the LED off. Okay, so let's upload it, and we'll see it in action. Okay, so there's our banner message. So I'll push the button, and we'll just have a look at what it produces. So there's the LED come on, and it was on very, very briefly, and then it's finished. So what we can see here is we see the starting message running of test 0, and so it says here that that took 0 seconds to print. And the reason for that is that this definitely will fit into the buffer. Actually, that was the message. Definitely fit into the buffer. So it's basically copying that into memory, which is very fast. And then it relies on the USART to send that out. And that's our report. So it says 0 to print this one. Now this 1 millisecond is for this one. So the second one says that this message number 1 took 0 millisecond. Sorry, took 1 millisecond. The next one, it took 6 milliseconds. So that means this one that's highlighted in blue took 6 milliseconds. And then it starts to settle down at about 28 or 27 milliseconds. And the reason for that is that we've definitely filled the buffer up at the first character. So there's no empty space in the buffer. These ones took less because there was a little bit of free space in the buffer. And as such, it could copy some messages in, or some characters into the buffer, and therefore the rest of the copy or the delay time to output didn't take as long. And then finally it repeats. Now if I hold the button down, I'll do a couple. You can see the effect here. So this is the first one, message 1, I'll run test 1. It's sort of similar, had a couple of zeros, then a 7, and then it sort of settles down to 27, 28, 29. But then, the next time around, it's 20 milliseconds from the first one. That's because there's still this other data from here in the buffer, the output buffer, because there's no delay between calls to this run test. It just keeps calling it. So this one also took about 20 milliseconds. The reason it's shorter is because there's less characters in it, so it doesn't have to wait as long to put the last character in. And then it's constantly 29, 28 milliseconds. Now if I push it again now, we should see the first pattern. Right, because the messages buffer is empty, and so it's able to print this out. Now the reason you might be getting 1 here as opposed to 0 like before, it could be that it just happened on a boundary. You know, we started at 0.9 milliseconds, and then the message or the copy returned at 0.0001 or something like that milliseconds. So it is a non-zero value, but the point is it's still very low. If I hit it again, hopefully we'll see. Yeah, so next time around it's 0. Okay, so we can see that's happening. Okay, and so again the reason for that is the first one, it just copies it into the output buffer and returns, and then the USART starts sending the data off to wherever, and ending up in this monitor window here. The next one, there's still some space free, so it only took 1 millisecond, so it got in there fairly quickly as well. Then it's starting to take a little bit longer as the buffer fills up, and then finally the buffer is full, so it has to wait the whole time. Now we can actually adjust it. If I perhaps remove that, make the message make it a bit shorter, we should see that these numbers drop down simply because the message is shorter and there's less data that it has to wait for the buffer to clear before it can put that in. Okay, so there's our banner. Push the button and we can see we got a few more zeros because there isn't so much data being shoved into the buffer on each message, so there's space for a few more, and then when the buffer did fill up, it still had to start waiting, but the time was much less because the message is much shorter. And that's sort of reasonable. I mean, just on visual inspection, it looks like it's about half the length, so it would be reasonable to sort of assume that it's about half the duration. Now, the other thing I'll do is just restore those messages, and we'll drop the speed. Now the reason I'm going to drop the speed is because I want to show that at the lower speed it takes much longer for these messages to come out, and in fact it'll take 4 times as long. So where this one came out in say 32 to, so what's that, about 200 milliseconds, this should take almost a full second. if I'm going to drop the speed, I actually have to change the number as well, not just copy and paste the line. So that's a sign that you've got a speed mismatch with the serial monitor, because we've had 2400 here, but it was 9600. Now it should be better. Okay, there we go. So what we'll be looking for, and you have to watch sort of fairly carefully, is that the LED, which gets turned on at the start of this function and then turned off at the completion of the function, so after the last message has been printed, what we should see is the LED turn on somewhere before it gets to the end. So the LED will turn off, meaning that we've exited the function, but messages are still coming through here. And the reason for that is because the last couple of messages will be stored in the buffer, and the hardware, the USART, will be sending it one character at a time and generating that interrupt to ask the hardware serial, or the serial object in this case, to give it the next character to send out. So you have to watch it fairly carefully, because even at this lower speed it still can happen fairly quickly. So here we go, I press the button in 3, 2, 1, there's the green LED, it's gone off, and there's still a little bit of message come out. So I'll do it again. So off, and there's still a couple of lines. One more. So it's off, but still, I think it was the last 2 or 3 lines. Now we can increase that effect by dropping it even more. I'll make it 1200. So upload that. Okay, so press the button, 3, 2, 1, press LED off, and then definitely you could see a couple of more lines come out even after the LED was off. And again, that's because of the interrupts and the output buffer that's managed for you by the serial device. So hopefully that sort of gives you some idea of what's going on there with the hardware serial, and also shows how through having that buffer it can do some stuff in the background without holding up the rest of your program, and your program can go off and do other things. Now, we're not doing very much, but if you were doing other things, then they would certainly be allowed to operate in the background. Okay, so next what I want to do is start working on a project that will generate a consistent signal, and as we'll see, I'm going to eventually use that and connect it up to another Arduino using a circuit like this. And so the idea will be that the Arduino on the left, which is the one that I currently have connected up, I'll use that as the sender, will send a regular signal to the one on the receiver. So as I mentioned, this is to sort of have a tamper resistant, perhaps burglar alarm system, or whatever. But the idea is that I'll send a regular signal across this purple wire, and then this guy over here will receive that. And we'll see that we need to use interrupts, especially if we're going to do other stuff, and especially if that other stuff occurs at random, like perhaps reading sensors or whatever. If we want this signal to be regular, then we need to use an interrupt to do that, to manage that. So I'll continue working with this one first of all. Now the other one didn't use the button, so we'll just ignore the button for now, and I'll modify or create a program that blinks these two LEDs in unison, and then ultimately this blue wire, which is connected to pin 4, will have the resistor removed, and it will become the signal. So there's pin 4, that'll become the other signal, and the receiver will receive it on pin 2. So we'll start with this side, and I'll continue to use the resistor, and we'll just get them to the two blinking in unison. So I'll save this one as the sender. Continue the naming convention. So sender, no ISR. We won't want that. Since they're running in unison, I don't need any other additional timer stuff, so I don't need the button stuff. Sender. Probably don't need that. And don't need any of that. What I'll do is put that logic in there. Okay, so what we'll do is just in our loop, we'll just continually check to see if it's time to send the heartbeat. If it is, then we'll remember the time we've sent it and then send the heartbeat. Just so we get rid of the highlighting. So yeah, we'll read the current setting, invert it, and then basically write that out to the signal and the heartbeat pin. Okay, so let's upload it, try that. So we have an error, signal, I don't think we need this one anymore. Okay, so no surprise there, we can see that both the LEDs are blinking in unison. Now, the problem with this will be that if we have to do some other things, it could disrupt this. Now, obviously, I'm going to create an artificial problem here, but I'm going to create this task called Big Task, which I happen to have prepared earlier. So I'll put that here. And all it does is output a message, then it outputs a series of dots with a delay of 100 milliseconds between each one, so this will take 4 seconds to execute. 40 times 100 is 4,000, and then it'll output a message saying big task complete. And what I'll do is I'll simply call that from here. So I just replicate this big task. As I said, that is artificial. I could use a different task here, and on the website I'll create one that outputs a multiplication table, so if it did a status report or something like that, that also can take a little while, and you get the same effect. So you can try the couple of different things, but the point is that if you run something that takes a little bit of time, what we'll hopefully see is it interferes with the blinking of the LEDs, which is this one. Report interval, report ideally this would also be a local variable, because we don't really want to do anything else with it anywhere else. Okay, so upload that, and the interval, const long report interval equals, let's do it once every 8 seconds. Okay, so I'll upload that and see what happens. And there we have it. So we can see the LEDs are blinking in unison. And now the big task has started, and so as a result the LEDs stopped blinking. And the reason, of course, for that is that if we call this big task, then we're entirely stuck in this big task function till such time as it completes, and so therefore this has no opportunity to execute. So what we'll do is we'll see if we can have the best of both worlds. We'll fix the problem that the big task is interfering or blocking the heartbeat function, and hopefully we get the LED blinking at the same time, or both the LEDs blinking at the same time in unison without interrupting the flow of the program. Now this will be slightly more complicated than the button one, where we used a simple function called AttachInterrupt, and we had a simple function, and it'll be a little bit more like some of the other code that we looked at in the Arduino library, where we were setting registers and things like that. I probably won't explain that in too much detail. Rather, I'll just refer you to the data sheet to understand how they work, but I'll briefly explain them as we go. Okay, so to start out, what I'll do is I'll save this again, so we have an interrupt version, or an interrupt-driven version. Now, the two main changes I need to make is in the declaration of the function. So I'll just comment this out. Actually, I'll also open the other one up so we have that available to us. Put him over there. And to make our heartbeat function a ISR, we can use ISR like the other code we looked at uses, or we can also use signal. And we need to specify the vector to comp a vect. So where do you get these from? It's a little bit challenging. I've never really found a definitive list other than the source code for the, in this case, AT328P mega include file, which is included when you compile it. So how do you find those things? Usually you just have to look for an example that references that there are files, header files that are included in the compiler that define them for you. But I usually found you can sort of work them out from the data sheet, or you have to find an example. So that's the one that we want for our systems. That's declared the function there, which was previously our heartbeat, to be the interrupt service routine. The other thing that we need to do is eliminate this. And of course we don't need the variables associated with that anymore. Now, the final thing we need to do is set up the interrupt in the setup routine. So before you do anything that might affect interrupts, the first thing you need to do is turn them off. And we can do that. There's a few different functions you can do that. This is one of them. And of course we also need to make sure we remember to turn them on. So I like to turn it back on here, and then put the rest of the code in the middle. And what we're going to do to enable them is just set a few different registers. So in the example that I'll put on a website, I'll have comments that explain what all of these are. But essentially what we're going to do is that, which just initializes the registers to where we want them to start from, and they're all zeros, so these are the ones that are actually counted. Now this is the compare match register. So what will happen is the counter will count upwards from 0 every time the other parameters are satisfied, and it'll count up to 249, and that's when it'll fire the interrupt. So effectively what will happen is once every, I think it's 1 millisecond, 100 milliseconds, we'll count it up. We'll fire the interrupt. This one sets a pre-scaler, so what it does is it sets the 64 times pre-scaler. So what that means is the 16 megahertz clock is divided by 64,000, 64, which means that the time will increment 1,000 times per second when we include the counter match value of OCR2A. And next we set some options that reset the counter. When it reaches the match, we reset it to 0. And then finally we enable the interrupts. So this is the step that enables the interrupts, and these others configure the timer. So that works out to be a 1 millisecond clock tick. And then the other thing that we need to do in our interrupt service routine, because it's happening much faster than what we want it to do so, we also need to do some counting. So our ISR is, what happened to our heartbeat interval? Still need that. Copy that back from there. So in our ISR, what we need to do is to have a counter. static int count equals to heartbeat interval, and we'll count down. Okay, so what that's doing is it'll decrement the count, which starts at 200 from this value over here, and if it's not 0, we'll just return. So you need to count 200 of these 1 millisecond interrupts, and then when it is 0, it doesn't return, so then it'll do this heartbeat. And so the first thing we should do here is reset it. So we've reached 0 and it's time to blink the LED, and so then we need to reset it so I can start counting down from 200. So this will implement effectively a delay of 200 milliseconds before it adjusts the LED. So let's upload it and see what happens. Just clear that output. Okay, so we can see it's uploaded, the LEDs are blinking, the big task is running, we can see the output and we can see the LEDs are blinking. So what's happening is our interrupt is being triggered, and even though the big task is running, which previously stopped the LEDs blinking, they're now reliably blinking at the rate that we've specified. Okay, so the next step will be to connect this up to our other Arduino. So we'll be moving to this diagram here, where we'll have one LED on the sender side. We'll connect the two Arduinos via this resistor, and then we'll have another LED on this side. Now, do we need this resistor? And the answer is no, we don't need it, but I prefer to keep it in there for safety. And the reason for that is if I accidentally upload a program which configures both of these pins, so 4 on this side and 2 on this side as output, and one happens to be set from high and the other happens to be set to low, then effectively what we've got is a short circuit. So there's nothing, no load, nothing preventing maximum current flowing through here, and that's going to burn out either or both sides of the Arduino, or very likely to. So I've put the resistor in there just to guard against that scenario. What we will have is this one is configured as output and this one is configured as input, not input pull-up. We don't need a pull-up resistor because we've always got a concrete signal coming across this wire. There's no chance for a floating input, so input is all we need, and we'll send the signal across there. So that's what we'll move to next. Okay, so if you're wondering how we work out these symbols, and these ones, generally they follow a pattern from the data sheet, so you can look at that and sort of work them out. I've never really seen a definitive list other than deriving it from the data sheet, but there is an include file which comes with the IDE. Copy this and then find that, and there it is. So that's the definition there. Timer to compare a vector is number 7, or vector 7. And with a little bit of luck, if we go back to the data sheet and we go to interrupts, then there, that's vector 7. So it's the 8th number, or it's the 8th one starting and counting at 1, but the addresses start at 0. So it's address 7 is timer to compare A, which, with a bit of luck, should match this. Yep, timer to compare A vector is address 7, which is that. Okay, so you might be wondering how to find this file. It's fairly straightforward. You just can start with one of these, like the W interrupts that we looked at just briefly, and start with its directory location. And so then the question is, well, how do you find this? So you can take any Arduino program and just get rid of that. And when you compile it, it'll tell you basic location of it. So if I just upload, not upload, but just compile. Now you've noticed I get lots of messages in my output. That's because I've turned on verbose output. So if we go to File and Preferences, then where is it? There it is. Show verbose output during compilation and upload. And that's useful for all sorts of reasons, one of which it tells you lots of useful information. That's the main reason. And one of those pieces of information is where those files are. So the one we're looking for is using core from platform in folder. Now obviously different systems are going to have different paths because this is in a sort of temporary working directory, and obviously on Linux and Mac it'll be different again. So just copy and paste that, and then go to our favorite preferred text editor, go to Open, and wherever you set the path, just paste that into there, and then they should be in cores, Arduino, and there they are. So there's hardware serial 1, hardware serial 2, hardware serial 3, and so on. Okay, and so from there, once we have that file, we just go to Open, and we back up to, let's see, Arduino 15, Packages, Arduino, back to there, and these files are in the hardware branch of the directory, and then these ones IOM 328p, so these are the microchip header files that have the configuration and all the constants and definitions for each MCU, is in the tools path. So then it's tools, AVR GCC, and we'll choose the latest one, 7.3 AttML. Then it gets a little bit repetitive, so AVR, include, AVR, and then we can see there's a whole bunch of them there. And so it can be a little bit hard to find, but in mine I can just type it in IOM 328, and there's all of the files. So that's the IOM 328p file, which, well, it won't open that again, so I'll just choose a different one. Perhaps this one, which is a very short file. And so that's another one. So that one just includes the IOM 328p. But anyway, that's how you find these files. Okay, so what I'll do now is add in this second Arduino as the receiver and hook the circuit up this way. So I think I'll begin by removing this button. That's just occupying space at this stage. Actually also I'll unplug the power. Don't want to create a problem because of that. Now I'll move this red LED over to this side, as that's where we're going to place it ultimately. So this will be our communications channel, and that will connect to pin number 2. Yep, that's correct. And then our status LED, might use a longer wire for that. We'll go to pin number 7, and I think that's it. No one more. We need to connect the ground up. It's always important to have the grounds connected up. So connect that. To there, so that's our ground, and then we'll use a little bridging wire to connect the two sides up. So it's important to have a common ground reference, because that's how the two systems can measure the signal. So when this is 0 volts, then obviously the signal will be equal to the ground, but when it's +5 or are high, then there's a relative difference between the ground and the signal on this communication, so that's how it detects the high. So it's important to have the grounds connected. There's very few circumstances where you don't need to have them connected, but this is definitely not one of them. Okay, so that should be ready to go. I'll plug this in, and what we should see is just the green LED flashing now, which is correct. And I'll plug this one in, which should have just the blink application on it, so we shouldn't see anything exciting happening now except for the inbuilt LED is blinking. Alright, so let's build out a receiving module for our simple little tamper resistant signaling device. And I think we'll start off with a new one, a new program. So to start off with, I'll just declare some constants. Okay, so we'll have the LED connected to pin 7 and the incoming signal will be on pin 2. So let's initialize those. So that's our initializations. As I said, because we have a definitive signal coming from another device, as opposed to a button that might have a floating input, we don't strictly need a pull up or pull down resistor, so we can just declare this as input. We don't want to use the pull up resistor built into the MCU or the Arduino's CPU. Okay, what next? I think as before we'll have our counter. So we have a counter and the system status to keep track of what's going on. Okay, so now the main logic. So what we want to do in this one is just simply have the LED follow the incoming signal. So I'll save the previous signal state, initialized at the same value from the first instance. So if the system status has changed or the signal has changed, then we just remember that for next time. And if it has changed, what we'll do is increment the counter and update the LED. And I think we'll output again a standard message that's indicating what's going on. This is where the counter comes into its own, because we can sort of see that the things are incrementing as we proceed. Okay, so let's just give that a try. Okay, so what we should see is the LED blinking and of course messages coming out here indicating that the signal has been received, or we might get an error, in which case try again. Yeah, so what we should see is the LED following the sending LED. Okay, so hopefully it's obvious that the LEDs are blinking in unison, as this one is turning this green LED off and on. It's also sending the status across this connection, which is being received here, and then our program is just in sync updating that. So let's add in a big task. So I'll use the same big task that we used before. I think I'll just put him there. And just need to introduce a few new variables to keep track of what's going on. So once every 8 seconds, obviously we need to keep track of the last time we did this. In fact, what I might do is make that 4,000 so we don't have to wait so long for it to start up. Okay, so I just upload him and see what happens. What we should see is that the LED will blink in unison until such time as this big task runs, and what we should see is the green LED continue to blink, but the red LED will stop while the big task is running. Okay, so we can see the red LED blinking, and then the big task runs, and so it stops until such time as the big task completes, and then it resumes again. And so that's the problem, because the big task is running. We're in this part of the code, in this part of the code, running this big task function. So there's never an opportunity here to receive the changing signal. So what we'll do next is try and fix that. Okay, so what we'll do is we'll just save this, continue the naming convention, and we just need to make a few minor modifications. So the first thing we'll do is add an ISR, not button. And what we want to do, I think, is just do the same thing as here. So we'll do this. We'll read the system status. And because the interrupt service routine is only going to get called under the same conditions as this, which is the system status changes, we don't need any of this if. But we still need to have this if statement here, because when the system status changes, we do want it to output this message, and so we can see, when we do finally detect that the system status has changed, we want to increment this counter. And that gives rise to something that we'll observe in the output. You'll notice here that it never skips a number. That's because in the previous version of the program, there was never an opportunity for this to execute when the big task was running, so the counter could never increment. But when, in this case with the ISR, it should be interrupting this big task and the counter should increment. So what we should see is that there'll be some gaps in the numbering. So for example, here it goes 460 to 461, or here 480 to 481. What we should see is it skips a bunch of them, so it should go to 480 to, I don't know, 490, 500, something like that. That's what we should expect to see. Okay. So what else do we need to do to it? Since these are being modified in the interrupt service routine, we should probably declare them as volatile. Again, in a simple program like this, it probably doesn't make a difference, but it's still a good habit to have. And then finally, I think all we need to do is attach the interrupt and then specify the ISR. Now, I'll just open up the previous version. I'll put him here. In this case, what happened is whenever the system status changed, so whenever it went from low to high or high to low, we updated the counter. And so we want to try and emulate the same thing here. And so the answer, or the correct parameter here, is change. So whenever the line changes, we want to fire this interrupt. That was slightly different with the button, which I think from memory is whenever we go low, we wanted to activate the functionality. Whereas here we want to do it on every change of the pin, which is reflecting what that if statement is doing here. So I think that's all we need to do. Let's upload it. Let's upload it and give it a try, see what happens. So again, what we should see is the pins, the LEDs continue to blink in unison, even if the big task is being output. And I think we can already see that the big task is running and the LEDs are still blinking in unison. And now we should see the gap. So you can see here it's jumped from 40 to 61. So this time it probably should jump from 80 to 101. Because the timing is consistent. Now, as I mentioned, we could make this into a tamper alarm. I'm not going to bother doing that. It's just a matter of changing the logic in here. Instead of just incrementing a counter, what you could do is capture the current time. Remember, it's safe to call millis from an ISR. It's not safe to expect it to change, though, but you can get the current time. And if you just remember the previous time, then you can subtract it and work out what the actual duration was. And assuming it's within a reasonable interval, then you can accept it. If it's outside a reasonable interval, then you can sort of raise an error or an alarm or something like that. And the other thing you can do with it is you could actually send a message across there. So you could encode data. For example, you might say that if the signal is 200 milliseconds, that corresponds to a 0. If it's 100 milliseconds, that corresponds to a 1, and anything else is considered to be an error. That's not the most efficient way of doing things, but you could do something like that. Okay, so hopefully that gives you a bit of an insight into interrupts. One thing that might be on your mind is when we set up the timer, which is over, I'll close him. When we set up the timer, we had to sort of set up these weird things here, and we had to set up this rather complicated, sort of unusual function definition, whereas in the pin receiving data, we just had a regular old C function and just called this attach interrupt. So you might sort of be saying, well, why is this so complicated and that's so easy? And the answer basically is that the folks over at Arduino have provided you this nice function which makes it easy to link into interrupts without having to bother setting this sort of stuff up and doing these weird and funky function declarations. But behind the scenes, that's still going on. So if you're interested in seeing that and reading through it, you can find the attach interrupt code in this file in the HAL, and again this can be found on GitHub and on your own PC. So where's the attach interrupt? Here it is, the attach interrupt. There are the parameters it takes. So the interrupt number, which is the digital pin to interrupt, the name of the function you wanted to call, for example, button ISR. I'll just reposition these to make it a little bit easier to see. Yep, so the signal ISR, and then the mode has changed. And basically all that does is it remembers it, the name of the function that you want to invoke in this thing called userfunc, in this thing called intfunc at the interrupt number, and that's determined by this digital pin to interrupt function call here. And then depending upon what mode you specify and the interrupt number, it will set these registers. So there's those sort of funky uppercase sort of variable names which you sort of don't declare anywhere. They're all in the IOM328p.h file, which defines the UNO. And then when you get down a bit further, this is where the interrupt functions are declared. So it uses this macro called implement ISR. I won't go through the if statement here, but this is the two lines of code that are set up for an UNO. And so we have the int0 vector and the int1 vector, which will be in the PDF. So we go to interrupts. So there's the int0 and int1 vector. And that macro is just this function here. So it will generate the code. There's the header, which we have in our timer function. So that's the same sort of header that we have here. ISR, I use signal, they use ISR, it's the same thing. And then the vector, which will be one of these, so int0 vect instead of timer to compare a vect. And then all it does is calls a function defined in this array, which is their intfunc, where our function, in this case, signal ISR is stored. So that's the only difference. It's still the same process. You have to set that up. It's just, as I said, the folks at Arduino have been nice and just given us this simple function that we can call to set everything up. Okay, so hopefully that gives you an insight into using interrupts and how and when you might want to use them for yourself. Obviously there's plenty of use cases that are valid, and equally there's use cases that are, perhaps not so sensible or appropriate. But again, hopefully that's given you a bit of an insight into some circumstances to when and why you might want to use it, which in all of these cases is generally that something has happened and it needs to be attended to in some way, usually making a note of it, or in this case, because the processing is simple, just dealing with it as it occurs, but we're also making a note of it by the fact that this system status variable is global, and then later on in our loop, when we finally get back to it, which is what's happening in this case after a big task is running, we can do something else to report on it, which isn't quite so urgent. And we can see that in the output there, where in this case it's skipping a few values because we're still registering the interrupt and dealing with it and detecting and recording the fact that there might be a problem with the signal, and then when we can get around to it, then actually dealing with reporting it, which is what's happening here. Okay, thanks for watching. I hope you found that was interesting and informative. And if you've ever used interrupts in your project or thinking about using them, it'd be great if you left a comment. I'd love to hear about how you're planning on using them, or how you did use them, and what your rationale was, and how they helped you, or maybe how they hindered you. And leave your comment down below, and I do read them. I find them very interesting to see what other people are doing and thinking. And also, if you could help me produce more content on all about Arduino, it would be great if you could like this video, subscribe to my channel, turn on the notifications so you'll be informed when I post new content, and contribute on Patreon and or buy me a coffee. I've put the links in the video comments below. And finally, have a look out for me on social media, including Reddit, Twitter, or X as it's now called, LinkedIn, and so on. So once again, thanks for watching, and see you again next time on All About Arduino. Bye for now.